I want to show one last optimization problem, and this one is going to be much trickier. And I'm not showing it to you because this is the kind of problem that you would be expected to do in an AP Calculus class or something that you would be asked to do on the AP Calculus exam. It's much more work than you would ever be asked to do under a test condition. But I want to show you that everything that you've learned in geometry and algebra and calculus can be used to solve interesting and somewhat complicated real-world problems. Let's take a look at what this problem is, and then we'll split the solution over a couple of videos. So we have that a power line is needed to connect a power station on the shore of a river to an island 4 miles downstream and 1 mile offshore. So we should find the minimum cost for such a line, given that it costs $50,000 per mile to lay wire under the water and $30,000 per mile to lay wire underground. Okay, so the first part of this problem is going to be some geometry and, maybe a little art to kind of draw a diagram of what the situation is talking about and figure out how to express this cost in terms that we can solve with calculus. So if you want to, either at this point or at any point in the video, try pausing the video and seeing if you can find your way to the next step. All right, so let me draw a diagram. So we've got a power station. I'll stick it here and I'll call it S. And we've got the shore of a river. This is a pretty wide river if it's a mile offshore. So I'm thinking this is more ocean than river. So the island is like over here. Okay, and so it's 4 miles down the river and 1 mile offshore. Okay, and we want to stretch a wire that goes from S to I, knowing that it costs a certain amount to lay the wire under the water. So if we went just straight, that would probably be super expensive because it would be $50,000 per mile for the whole mile. But the other way we could think about it is maybe there'd be some point like over here where the wire would go down the shore, which is only $30,000 per mile. And then at that point, it would jut out and just make a straight run to the island from there. So the idea is, where should this dividing point be that makes this total cost as low as possible? All right, so in order to come up with some equation for that, the first thing we need to do is we need to come up with a variable x somewhere that expresses, some level of this variability. Okay, and what I'm going to decide to do is I'm going to put the x right here. So this is the thing that changes, the distance from this branching out point to kind of the projection of the island against the river. You could make this x over here, but then this thing over here would be massively ugly. Okay, so how long is this distance given that this is x? Well, this whole distance here is 4 miles. So this section here would be 4 minus x. And what is this distance of the length of the wire that would go underwater? Well, we've got a right triangle here, and we know the lengths of 2 of the legs. We don't know this length, but we've got an expression for this length. So we would use the Pythagorean theorem. So this leg would be the square root of x squared plus 1. All right, and the last thing that we need to figure out is, what should our cost function be? All right, and just to make things a little bit easier and not to have to carry so many variables around, why don't we say that C sub x is the cost in thousands of dollars? So we know that whatever answer we get, we'll just multiply that by 1,000 to give us our answer. So that'll have us just having fewer zeros that we're writing. All right, so based on the problem that we've got right now and the diagram that we've built up to this point, what is an expression for C of X? So C of X, so this 4 minus X is the amount of wire that's being laid underground, which is $30,000 per mile. So it would be 30 times 4 minus X plus the cost of the wire that's running underwater. And so that costs $50,000 per mile. So that's 50 kilobucks times the square root of X squared plus 1. And maybe we'll just simplify this a tiny amount. So we'll do the distributive law here. So it'll be 120 minus 30x plus 50 times the square root of X squared plus 1. All right, so there's a good point to to end this first video. So in the next video, we're going to take that hideous looking function and we're going to be able to find the maximized value of it by taking the derivative of that function.